Hey everyone, in this presentation, determination of nearly mode 2 fracture resistance in a multi-directional carbon fiber reinforced laminate will be discussed. The outline of this presentation will begin with an introduction of the investigated composite and interface. The calibrated and loaded split specimens which were used in the nearly mode 2 fracture toughness tests will be shown. Results from these tests will be presented, and the analysis methods which were used in order to obtain the initiation and resistance energy release rates will be explained. And finally, the R curves which were obtained by means of each method will be presented and compared. Then the work and results presented will be summarized. So I hope you will enjoy this talk. In this research, a composite laminate is investigated. A laminate is composed of several plies. Each ply consists of fibers embedded in an epoxy matrix. The fibers within each ply may be oriented in different directions or in the same direction. In addition, the different plies may be the same or different from one another. In such a composite, there are two main failure modes. The first is matrix cracking, when the crack propagates through the matrix, through the epoxy. And the second and most common are delaminations. A delamination occurs when two adjacent plies tend to separate, and in this research the focus is on this failure mode. So in order to use fracture mechanics concepts, the two plies adjacent to the delamination were homogenized and described with their effective mechanical properties. The specific material and interface studied in this investigation is composed of an upper unidirectional composite ply with mostly T300 carbon fibers oriented in the 0 or the X1 direction, and some glass fibers oriented in the transverse direction. The bottom ply is a plain balanced weave with interlaced toes in the plus minus 45 degrees directions. The calibrated and loaded split specimen shown here is the same as the double cantilever beam specimen and composed of two arms which are separated with an initial delamination of length A0 from the load line to the delamination front. As you can see, a load block is attached at the bottom of the specimen to be used in the test. Here you can see a schematic illustration of the CLS test apparatus used in the fracture tests. The load is applied to the specimen through the load block by means of an Instron loading machine. The load block is pulled up vertically through a pin, and the clamping arrangement creates free horizontal sliding of the specimen by means of bearings, but it restricts vertical movement. Here you can see the test setup. The specimen is in the fixture. The slider is free to move in the X1 direction, and the specimen is attached to the clamp with retaining bolts. The loading grip is attached to the specimen through a pin and is pulled up quasi-statically in displacement control throughout the test. The load throughout the test is measured by the load cell, and the relating actuator displacement is also recorded throughout the test. In addition, a vision system composed of a light, a camera, and a programmable timing unit is applied during the test, and images of the specimen were acquired where on every image the load and the displacement are synchronized and displayed. In addition, During each test, the relative humidity and temperature were recorded. The fracture resistance tests were performed in two stages. In the first stage, the delamination propagates from the insert. This stage is referred to as the artificial crack, or AC stage. Here you can see the load displacement curves, which were obtained for 6 specimens from this stage. In the second stage, the delamination propagates from the pre-crack. It is referred to as the PC stage. The pre-crack was achieved during the first stage, and here you can see the load displacement curves from the PC stage. It may be observed that there are variations in the stiffnesses of the different specimens. The reason for this may be a result of the differences in the initial geometrical conditions of each test, or perhaps they may be related to the wet layup manufacturing process of this material. The results from the tests were analyzed by means of two methods. A global method, referred to as the experimental compliance method, or ECM, and a local method which makes use of the J integral. The ECM begins with a relation between the compliance and the delamination length throughout the test. So this is the assumption for this relation, and the compliances for several delamination lengths are calculated from the load and displacements which are related to each delamination length. And using this data from the test, the fitting parameters M and C0 are obtained. In order to calculate the energy release rate, the Iron-Keyes relation was used, and the derivative of the relation which relates the compliance and the delamination length was found and substituted into the Iron-Keyes relation, so that finally a relation between the energy release rate, the applied load, and the delamination length is obtained. And using this relation, R curve was found for each specimen, and finally a global R curve was obtained. The second method used was based on finite element analyses along with the J integral. For each specimen, 4 two-dimensional finite element analyses were carried out with A0 equals to 50, 60, 70, and 80 millimeters in each analysis. For all analyses, a displacement value of D equals 10 millimeters was applied, and values of J at D equal 10 millimeters were obtained for each delamination length. So these were found from the different finite element analyses. The values, the J values, were normalized with respect to the load obtained at D equals 10 millimeter for each analysis, and J hat were obtained for each delamination length and plotted, as you can see as the blue dots in this figure. A parabolic fit between the 4 data points was found and used to obtain a function for J hat for any delamination length. In order to find J, which is related to the test results, the normalized J hat was multiplied by the load squared, which caused delamination propagation during the test. So now we have a relation where for every delamination length measured from the images which were acquired during the test, and the critical load which is known from the synchronized images, J may be calculated. So using this relation, again, an R curve was obtained. By means of each analysis method, an R curve was obtained. Here we see the resulting resistance energy as a function of the delamination extension as it was obtained by means of the experimental compliance method. The points are the individual values obtained from the 6 tested specimens, and the black curve is the final R curve which was fit to the data. Here are the results obtained using the J integral and the finite element analyses. In both cases, the R curve begins with an initiation critical value, G2C, which in both cases were obtained for each specimen based on the artificial crack stage, the AC stage. And they were obtained by means of finite element analyses with the J integral. As the delamination extends, the curves increase until a steady state value of G2SS is reached, and using these curves, delamination resistance to propagation may be predicted. Here, a comparison of the two curves is presented. In blue is the R curve obtained by means of the experimental compliance method, and in red, the one obtained from the J integral. Since the two curves are quite similar, it is possible to conclude that the J integral local approach provides results which correspond well with the global ECM. Also, it may be noted that the local J integral approach resulted with a more conservative curve than that obtained by means of ECM. So to summarize, the material investigated included a delamination between an upper unidirectional ply and a lower woven fabric ply. 6 CLS specimens were tested with nearly mode 2 deformation, and then finite element analyses were performed for the AC stage as well as for 4 different delamination lengths. By means of the J integral and the experimental compliance method, the critical and resistance energies were obtained and plotted versus the delamination extension. These resulting curves actually are important in order to predict delamination resistance to propagation. Thank you for listening to my presentation, and I will be happy to answer any questions.